Yeah, look at we'll start in the upper left. Look at 2015
And these are the first, this is January through March of
surface temperature.
the
So that's
past
going to be
5
air
years.
temperature. So, yeah, so that's going to be air temperature. So not no sea surface temperature.
Okay.
Look, look at the eastern U.S.
Wow. 5 years
Really
ago.
cold, really
Really
cold
cold.
and unusual. That goes back to what I was talking about earlier with the NAO and the AO being in negative phase and the meandering jet stream brought the polar vortex down.
Wow.
There it is.
And that's
That
the
was,
last time there is, you could see what the other ones real quick. That's the last time you see some blue. But go ahead.
yeah, pretty much. I mean, but you can, I mean, look at 2016. Okay, we know 2016 was the warmest year for overall for the entire planet. But look how warm the Arctic is. In fact, look how warm the Arctic is in 2017, 18, and 19.
Okay, so at the top of it says 2016, the warmest, the 1.30. That's 1.3 degrees Celsius.
Correct.
Oh wow, that's, and remember the threshold. I mean, globally, right? The all 12 months we can't get above 1.5, but that's the winter in the northern hemisphere, and it's not looking good.
No,
Oh my
a
goodness!
lot of that is due to the heat energy given off from the open sea, no sea ice.
Wow.
We have, especially if you look at Alaska, look at 2016 and 17, look how warm Alaska is because you have that heat energy coming off from the unfrozen Arctic Ocean and Bering Sea.
Oh my goodness.
Latent heat energy will help warm things up. But even still, you can still see in the North Atlantic, just off the southern tip of Greenland, you can still see a little splash of cooler than usual. That's because of the meltwater coming off Greenland that will then cool the air above it.
Right. Once again, this is air temperatures.
This is air temperature. So you've got the Greenland is melting. So you have the cool water. You have the water spilling into the ocean. It's cool. It's going to cool the air above it.
How interesting. That's really important that you pointed that out because it does show you that
And
the
that's kind of
coolant,
also
yeah,
where
the
the
coolant.
NAO tends to be centered.
Oh my goodness.
And that's also where uh, where the terminus of the Gulf Stream occurs and so on. But yeah, so that's why you tend to consistently see that little cooler than usual spot right there in the Atlantic, is because you've got the meltwater from Greenland cooling the air above it.
And if you go to 2020, it says we're the second warmest, 1.2 degrees
Well, look,
Celsius.
and look at how cooking Siberia is, right there in the
Right, the
middle of all
bipolar
that dark.
polar. Yeah, it's
And you can
that's not good.
and you can see how it's cooler over Alaska and over basically like Ellesmere Island and some of the Canadian archipelago. Again, tying into that bipolar polar.
But
So
going
yeah,
back to Siberia, you could see that like lavender purple shade, light purple shade is over the landmass, whereas in the past few years it's been over the water.
that's correct.
What are the
Yeah,
consequences of that?
of being warm. Well, it will start thawing out the permafrost a lot faster, which means methane gets more and more that gets released. That's an immediate consequence of what's happening in Siberia.
Oh my goodness.
And of course, methane, even though it doesn't last as long in the atmosphere as carbon dioxide does, it's about 20 times more potent a greenhouse gas than CO2 is. So it has more heat trapping capabilities.
If this doesn't scare you, I don't know what will. You know what I mean? Like, or at least frighten you or make you aware of this. This is concerning based on once the permafrost goes, we're talking about 10 degrees Celsius global average temperature. That's, we're gone.
If you want to know what 1.3 is C in Fahrenheit, just multiply by 1.8.
Okay. Oh my goodness.
Yeah. So let's see if I can do
Yeah, I
the
got
distributive 5. 1.3 plus 2.4. It's about 5.7 Fahrenheit, something like that. Did the distributed property in my head.
You know how to do the calculations. I'll let you do that because I'll screw up the data. Shoot.
It's warm.
It's warm. Real quick, with the 2020 second warmest graph, look at the, if you could see, there's like a red blob, like where off the coast of New Zealand. I remember doing a
Oh
video
yeah.
that I thought, isn't that like where the oceans are warming? I know that's air temperature, but that's
I can't say for sure, but
okay. Yeah.
I would need to look. I think that might be tied into the Arctic Indian, the Indian Ocean dipole. I'm
Maybe.
looking at, if you look at 2018, okay, look at the equatorial Pacific.
Right.
You can see that was La Nina,
Oh yeah, the blue.
right?
There you
Now
go. Yeah.
look at 2019 into 2020. 2019, we had a pretty strong El Nino situation. It's a little, looks like a kind of breaking down the El Nino into maybe neutral, and then we see a red blob. The El Nino and the Indian Ocean dipole tend to be coupled together. So I
Oh,
have a funny, my supposition would be they're tied together.
okay. So interesting and disturbing for obvious reasons. Um,
But if you look at 2018 and 2019, look at the Chukchi Sea, that
oh.
really pink stuff there. Look how warm those oceans were.
Which coincides back to the graphics we talked about with the sea ice extent for individual years.
That's right. Very, yeah, that's right. Excellent. Yeah. Basically, uh, the last 3 years, 18, 19, and now 20, are showing the lowest sea ice extent. When you start seeing warm temperatures like that, yeah, no surprise, there's not much sea ice,
Shoot.
and
Yeah.
hence a reduced sea ice extent. And even with the cool winter that was just experienced in Alaska, because of the thermal and energy still contained in the water, specific heat. Yeah, there's a little blip where the ice extent was above the 30-year median, but then the heat energy quickly melted that and it's quickly diving down. Extremely telling.
Right. You have what we see is has an accelerating warming period. Uh,
What I like is he places the horizontal, I guess, dotted line there,
yeah.
towards the right side of the graph, and it's identified as the 81 to 2010 average. That's a 30-year average.
Oh wow.
So, so now you do the math there, and we're basically almost a full degree above that 30-year average. Puts it in perspective, I think.
Yeah, that's not
It
good.
tells you that most of the warming is recent, is what it's telling you. Now,
It's just shocking. Go ahead.
I
Yeah.
also find interesting is if you look towards like 1860 there, okay, you see the line there, and you see that light blue shading around it, and that persists until about 1980, a little bit into the mid 80s. Okay, that's basically the error or the variance around the data, because there's some uncertainty as to the accuracy of the data.
Okay.
Then starting from about 1980 or so, you got a whole bunch of different data sets overlapping, but we don't see any shading, so there's no like confidence interval, meaning that yeah, these are pretty accurate measurements. That's what that's telling you,
What climate change?
right? I
I don't
mean, if you were to look, if you can start at 1920, if you were to put a line through, you have a positive slope. And if you start at 19 late 70s and 1980, that's a major positive slope. So now it's 40 years.
and it's supposed to keep going up,
Yeah.
which is just
And you see what it says,
Mind-boggling.
increase above pre-industrial baseline.
Oh my goodness.
And that's about, according to this graph, that looks like about 1.2, 1.25 or so, which gets back to about that 1.3 we discussed earlier. C.
And remember that the threshold, right, from the Paris Accords that are.
Well, the Paris Accord, they're basically trying to say keep it to, less than 2, ideally less than 1.5. Good luck. I don't even think that keeping it under 2 is possible.
I don't think so either. I mean, we're talking about 4 to 5 degrees Celsius in like 80 years. So that's a
Yeah.
significant. I don't even want to know. I mean, if you can survive, I don't know what
I
that
just
world's
came
gonna look
across
like.
I just came across an article that I'm preparing where they talked about how, the polar regions could be forested again. Antarctica could be forested again like it used to be. Yeah, when it was at about 70 degrees latitude, not 80, 90.
I know, right? They always try to do a positive spin again, right? It's
It's like, but
uh,
still, it's like, I've noticed this a lot. This is paper out of peer review. It's like, did you take into account plate tectonics? Through the positioning of the continents?
no.
Did you take into account what the ocean basins were like, what the oceanic circulation was like? Because that's going to affect weather patterns and precipitation patterns. And so there's some interesting things in the article, but there'll be some things I'll be critiquing.
Okay, that's what you do. That's how it is.